Kia ora tātou. So this is a project that Chris Moy and myself have been leading and has a number of years to run now. It's a 5-year program, although we've been working on it for kind of 10 years before that. But the current funding cycle is 5 years, looking at the carbon being buried in the fjords and investigating what the climatic and environmental controls are on that carbon burial and the degree of sequestration, to know whether or not this carbon sink's a really important thing and how resilient it is. We're also seeking some international funds from the International Continental Scientific Drilling Program to recover long records so that we can actually get back into previous times before the last 10,000 years, because we know that climate was changing significantly at that point. Just as a kind of acknowledgement, this is a big team. There's a lot going on. So you'll have seen some of these characters already, but these are just some of the main characters in it. We've got collaborations with international universities, working quite closely with Ngāi Tahu, with the Fiordland Marine Guardians, and also with ICDP partners. So it's a pretty big group of people. Most of the work is based off the Polaris, the University of Otago vessel, but also other vessels at various times. When we come to try and collect some long records, they'll have to be perhaps from platforms or bigger vessels. So why the fjords? Well, this is really interesting, not particularly well known, but some recent papers just here to refer to. But basically, the degree of organic carbon burial is high in fjords. The top diagram there just shows the amount of carbon being buried in different environments, non-deltaic continental shelf, deltaic continental shelf and fjords. It doesn't look so big at the top, but when you correct it for the area, it's huge. It's by far the biggest per area burial of carbon in the marine environment. So it's a significant carbon sink, and that's globally. So that's a global study. It includes Fiordland as well. So then could this be a potential solution for what we're trying to do in terms of redress the balance of carbon on the planet? This program called Carbon Watch, it's a program run by NIWA and GNS Science and others, has been trying to measure the degree of carbon in the atmosphere and try and assess whether or not across New Zealand we're dealing with a sink or a source of carbon. And you'll see the dashed circle around Fiordland there. By far the biggest sink is over Fiordland, which just goes to show we used to think that old forests didn't sequester carbon because they were in balance. Well, that's not the case for Fiordland. It is drawing down a lot of carbon. And this is why lateral transport. The carbon is coming out of the forest and being buried and sequestered somewhere else. So it's actually being drawn down rather than sitting as leaf matter or on the forest floor and then oxidising and becoming CO2 again. It's actually being transported out of the forest and buried into the fjords. So the dashed red line there is just showing you really in estuaries, tidal wetlands, well, the fjords are just really large estuaries, and they are burying the carbon. And in terms of the lateral transport of carbon, in this case here, over 1 petagram of carbon per year, well, that's the bottom asterisk there, that's 1 billion tonnes of carbon. That's a lot of carbon. Well, these are global numbers, sorry. And 45% of that's being sequestered into various sedimentary reservoirs. Sorry, those are the global numbers, not the Fiordland numbers. Now, in terms of Fiordland, we'll take a look at that. Of course, these are the areas we've been with the yellow dots there and the blue dots. They're particular samples that we've taken. But look, we're dealing with a very strong freshwater cycle here, 6 to 8 metres of annual precipitation, and that's very highly climate linked, right? So that's a climate driver that's moving the carbon out into the fjord. Then we've got that estuarine circulation, we've got that pervasive low salinity layer, and of course the forest. We've got a lot of active seismicity, so a lot of stuff being moved down into the deep through shaking. The steep topography and so on. It goes on and on. There's all these characteristics that are really important for moving the carbon into the fjord. And then once you get into the basin, this is just a depiction here. You've got this mixed layer, fresh water, then a mixed layer, then the marine water coming in. Fresh water's going out of the fjord from right to left. The marine water's coming into the fjord, and then in the bottoms, in these deep basins, 400 metres deep in most cases, anoxic sedimentary layer. So that's where, you've got no oxygen, you're not converting the carbon to CO2, and you're burying it as raw carbon. So what we're trying to work out here is, okay, how susceptible is that, and how much carbon have we got in there? In terms of pathways, you've all been in there, all sorts of ways that this carbon's getting in there. Yes, there's air-sea flux and there's carbon coming in from the marine environment, but there's a lot of it moved by particulate carbon in the waterways. And there's a lot of it moved by just shedding of forest into the fjords, either from rain events, like you can see here, just whole hillsides of forest falling into the bottom, or from earthquake shaking. So there are a number of different contributors. And if you do the basic back of the envelope, and we're only at the back of the envelope stage, this is the size and scale of the Fiordland sink. So left-hand side here, this is the measurement. We've just used this as 100%. This is the New Zealand annual emission of CO2. Only CO2, not methane. So that's the measure. In the brown there is how much carbon is sequestered into Fiordland from the assessment, from the Steinkamp measurements. That's more than our annual emission of CO2. So that's huge. And the measurements we've made so far would show that actually a big part of that's particulate organic carbon getting through the waterways and being sinking down and being buried in the fjord, but also the landslide removal on the right-hand side. At the moment, we don't know what the marine contribution is to that. So part of the study is to try and work out those numbers to some degree, as well as their susceptibility. So, that's huge. This is a really significant carbon sink. It's got a lot of value associated with it because we trade in terms of carbon, in terms of our emissions. So this is actually really rather important. Looking at the right-hand side there, and this will cycle through just a bit of the pathway of the organics getting in. But as we dive under the water here, look at it. It's really brown. It's full of particles. And as we pull up the mud off the bottom, it is black. It stinks. It's really, really anoxic. So that is the black gold that we're talking about. That carbon sink may be able to offset, or does currently offset, 20 to 50% of our annual emissions. So that's a significant amount of carbon drawdown. So the project that we're working on is really trying to do several things here, and I'll run through them quite quickly. The first is actually build a budget. How much carbon is going down, and can we track the methods of it getting in there in terms of source to sink? So what are the pathways that it gets in there? And then forward model, forecast out, and see how much we can project that's susceptible to changing climate, changing freshwater input. Obviously, freshwater is a huge part of this whole system. So how's that going to change? And part of that is by drilling down through the records. If you actually go to the bottom, it's layered up year by year by year in the bottom of the fjord. So if we can get back into the pre-Holocene, so 15,000 years ago, we know that at that point climate was changing quite rapidly. So get some idea of actually how the system responds to a changing climate. And then lastly in the project, actually use these results to help us manage that environment and see if we can actually put some protection if we need around carbon, or just understand what it is. How are we going to make sure we protect that carbon sink? Because I've been known to say many, many times, we can talk about emissions, but the real problem is carbon dioxide in the atmosphere. And there's a whole lot of natural processes going on that we need to protect as well, not just deal with our emissions. So just to give you some idea of the work that we're doing, in terms of that quantitative carbon budget, a lot of geophysical characterisation to try and picture what's at the bottom there, and image what's at the bottom. I've got an image coming up looking at carbon burial rates there. in terms of the source to sink, looking at trying to track where the particles are in the system with sediment traps, catchment and data as well, and trying to connect that up. In terms of the longer record and evaluating future carbon sequestration, here on the right-hand side you see the seismic image. Yes, it's about 300 or 400 metres down to the bottom, but then there's another 300 or 400 metres in places of sediment. So there's huge amounts of sediment in the bottom of those fjords, and that's what we want to target to get the longer records. There are some broader research opportunities that drilling can bring as well. I've talked about understanding carbon burial and sequestration, but these are really high resolution records of climate from a really important part of the world because they sit in the middle of the southern hemisphere westerly winds. So that's what brings all the rain in. We can talk about timing and impacts of sea level rise, and a big project we're trying to get GNS working on with us is actually the statistics around seismicity. How often do these earthquakes happen, how big, and how do you build a forecast around seismicity as well. So there's quite a lot coming out of that. And just to finish, there's huge societal relevance out of this stuff as well. Yes, maintaining and enhancing natural carbon sinks are as important as emissions. I can't say that enough. And they may have significant economic value to New Zealand. You only need to look at the numbers, okay? This sink is as big as our annual emission, so it's important. Changing freshwater fluxes do affect coastal oceanography, ecosystem structure and productivity. I mean, that's also something that leads into the type of work Rob and others were talking about. Yes, the seismic hazard mapping and understanding the seismic hazard models, changing coastlines, and then lastly, can we build this into actually what we do about carbon rather than the current approach, which is carbon sinks, they just happen naturally, so we won't build them into any carbon trading or understanding of our emission, when actually we need to protect and understand those as much as we do understand our emissions. Thank you.